Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will derive a formula for a credible interval for the difference between mu1 and mu2, where mu1 and mu2 represent the means of two independent normal random variables. We will assume that sigma squared, the variance for these two normal distributions, is common and known. Okay, so we're going to be assuming that mu1 is the mean for a normal distribution, but the variance is sigma squared, and we're assuming that is known. And we have a second normal distribution with mean mu2 and variance sigma squared as well, and we're also assuming that sigma squared is known, right, in that case, and those two normal random variables are independent. And after we derive that formula for the difference mu1 minus mu2, for the formula for the credible interval for mu1 minus mu2, we will also talk about how to carry out hypothesis test in this case. Okay? Well, so that's the ultimate goal. Okay? Finding a formula for the credible interval for that difference between two means of two normal random variables. The assumption is that the variance is the same and known for both of them. To obtain that formula, let me remind you something that I'm sure you have seen before in another course, to be specific in a probability course, for instance sta313. So let x be a random variable with a normal distribution. Let me use mu x to represent its mean, mu sub x to represent its mean. Let me use variance to represent the variance. I'm going to be using the following notation: sigma squared sub x. Okay. Then we have a second random variable, let me call it y, also normally distributed, different mean, different variance. Okay. Another assumption that we're going to have is that x and y are independent, okay. And next, what we're going to be doing next is we're going to be defining a new random variable like this, the difference between x and y. Okay. And what we would like to do here, and again this is an intermediate step, so we can derive that formula for the credible interval for mu1 minus mu2. We want to find the probability distribution of W. Okay. So we know that we have different ways. We learned about different ways of doing this in our probability course. One way, which is really convenient in this case, it's going to be really fast, is using an MGF. Okay, so we are going to find the MGF of W, that new random variable that we defined, and what we're going to see, as you can imagine, since we have a linear combination of normals, we're going to see that the MGF of W will be the MGF of another normal. Okay, and as a byproduct of this, we are going to obtain its mean and its variance. Okay, so solution. Let's find the MGF. So by definition, okay, we will find the MGF, moment generating function, of W. By definition, the MGF of W, let me use that notation, M sub W evaluated at t is just an expected value, the expected value of e to the power wt. Okay. Now, by the way, w is defined, that is the same as the expected value of x minus y. Okay, no problem. Now let's do a little bit of algebra. This happens to be the same as the product of two exponentials. Okay, the product of e to the power t, well, xt times, let me have another exponential here, let me copy this, and this one is just going to be minus yt, right? So that exponential is the same as the product of these two exponentials, right? And here's where the assumption of independence is really important, since we have the expected value of a product that is the same as the product of expected values. Okay, so now I have this, right? And that's thanks to the independence that we have between x and y. Okay, now one more step. We could think about this as follows. This is the same as y times negative t. Okay, and that's important for the next step. Clearly, the first term, the expected value of e to the power xt, is by very definition the MGF of the random variable x, right? So let me use that here, and this one here, it's almost the definition of the moment generating function at t, but no, instead of a t we have a negative t, so it's the MGF of y evaluated at negative t. Okay, so now we know, right, from our course, our probability course in probability, from our what we know about our probability courses, right, from sta313 for instance, we know that the MGF for an exponential with mean mu x and variance sigma squared x is going to be this. Let me use this notation, it's going to be easier. It's the exponential e to the following power, right? It's going to be e to the power mu sub x times t plus and then here what we're going to have is the following. We're going to have t squared divided by 2, and here we will also have well, let me place it here outside, sigma squared of x. Okay, that's something that we learn in a probability course, the expression for the MGF of a normal, right? And we could find it also, you know, in any probability theory textbook. So we have something similar for the other one, for the other variable that we are interested in here, for y. So let me change that one. The mean for that one is different, but now instead of a t we have a negative t, and again instead of an x there we have a y, and here we also have a negative t. Okay, so now we can combine these terms, right? We could have a single exponential, right? We have the product of two exponentials, so it's just going to be, all we have to do is add these exponents. Okay, so let me just keep one of these guys, and then for the first one let me factor out the t. Okay, so I'm going to have mu sub x minus mu sub y times t, right? That's the same as these two guys. Okay, now minus t squared is the same as t squared, right? So t squared divided by 2, that's a common factor, and now what I have here is plus, and I have that guy. Ready? Okay, so now if we compare that expression with the MGF of a normal with mean mu and variance sigma squared, well, guess what? This corresponds to the MGF of a normal, right? But now the new mean is mu sub x minus mu sub y, and the new variance is the sum of the variances, right? So let's just conclude, right? So first, by the uniqueness property of MGFs, we have that W has or that W is normally distributed with mean. The mean is going to be this guy, and variance this guy. Okay, so this is what I wanted to show. This is the result that is going to help us find that formula for the credible interval, that if you have two independent random variables with a normal distribution, okay, then the difference has a normal distribution as well, and these will be the parameters. Okay, so now let's go back to our main problem. Okay, So again, very important, right? Let me remind you that we are assuming that the variance sigma squared is known. Okay, let me again here where we talk about the conditions that we are considering. Conditions, sigma squared known, the variance okay, we're assuming that we have a sample. Let me call it sample 1, or another way of thinking about it is that we have a likelihood, right? That looks like this. It's we're going to have a sample of size n1, so let me use a double subscript here because we are going to have two samples. So that's the first observation from the first sample, and then I have a second observation from the first sample. I could have a third, right, for the first sample, and so on, right? And we are going to have n1 coming from the first sample. Okay, makes sense? Are we good? So again, the second subscript here is referring to the sample we're talking about. Okay. Okay, so in those guys we are assuming that we have a normal likelihood, and these guys have a normal with mean mu1 and known variance sigma squared. Okay, so now if we want to analyze that, if we want to say something about that parameter mu1, if we want to analyze that parameter from a Bayesian perspective, we need not just a likelihood like we have here. This guy is our likelihood. We need a prior, right? So our prior distribution, which is going to be using our symbols, it's going to be probability that a probability distribution for mu1, right? Well, we are going to be considering a normal with mean m1, right? That's our prior mean, and prior variance is 1 squared. So once we have our likelihood, right, and our prior, let me just mention that this guy represents that sample, is going to be, you know, where the likelihood comes from. Our posterior is just, we know, a combination between likelihood and prior, using the Bayes theorem to combine them, right? So now we have the posterior is the probability of mu1 given our sample, so we know that in this case, when we have a normal likelihood and a normal prior, we know that the posterior is also normal, and we use an m star to refer to the mean of the posterior distribution. Okay, so let me call it mu1 star, and we have also a variance, a posterior variance, right, which is going to be S1 star squared. Okay, so just like we had a first sample, right, since we want to study two means from two independent normal random variables, we are going to have a similar situation for a second sample. Okay, so let's recycle this. So we have a second sample. Now I'm going to have something like this: first observation for the second sample, second observation, third, and then we could have potentially a different sample size here for the second sample. Okay, so n2, and this guy with a mean mu2 but the same variance, same known variance sigma squared. Okay, so just like before, we need a prior for that parameter of interest, mu2 in this case. It could be, we could you know, have a different prior for that second parameter mu2. And by the way, we are assuming that these samples are independent. We are also going to be assuming that these two priors are independent. Okay, so anyway, once we have our normal likelihood and our normal prior, we can obtain our posterior for the second parameter mu, right, like this. Using our updating rules, we could easily show that, you know, the posterior is going to be normal. Okay, so there we are. So why did we talk about that preliminary result at the beginning of this video? Because remember that in Bayesian statistics, right, we think about parameters like in terms of, we consider parameters as random variables. So if we want to say something about the difference mu1 minus mu2, that's a random variable. So it's a situation like this one. And we have two random variables that are independent, right? And we want to say something about them. They have a normal distribution. Well, we know what's the behavior of the difference between, we know what's the behavior of the difference between two normal random variables that are independent, thanks to what we did here, right? We know that this difference has a normal distribution, and we know the parameters for that normal distribution. Okay, so that's exactly the situation that we have here, right? After we do after we update our knowledge about the parameter mu1 and mu2 using our prior and our likelihood, we end up with a posterior that has a normal distribution for mu1. We have a posterior that has a normal distribution for mu2. So if we want to say something about mu1 minus mu2, let's apply what we know. So let me just remind you that the samples, sample 1 and sample 2, are independent. We have two independent random samples, and the priors are also independent. So if we want to say something about, and let me label that difference that we're talking about here, let me call that mu sub d, to refer to the difference between mu1 and mu2. Okay, so let me say something here, some notation. Now after we observed these two samples, sample 1 and sample 2, these two guys will have, well, not these two guys, but the difference between these two guys is going to be normal. And thanks to what we did with our MGFs, we know that the mean for that new normal is going to be mu1 star, well, m1 star minus m2 star. And the variance for that difference is the sum of those variances. Okay? So, given that this guy, right, the posterior distribution of mu sub d has a normal distribution, if we want a credible interval for the difference, the formula would be the following. We would have this guy plus minus a critical value from a normal 0, 1, right? So let's let's find a critical value that has an area of alpha divided by 2 to its right and to its left, okay, times the standard deviation. So it would be the square root of this guy here. This is our variance, so we need the square root of that guy. And that's it. That would be the formula for the credible interval credible interval for difference between means. Okay, make sense? Okay, so we're done with that one. We have derived that formula. Now let's just say something about the other problem we said we were going to be talking about, we would be solving here. How about one-sided Bayesian hypothesis test for this situation? So say that you wanted to test something like this, okay, that the null hypothesis is that mu sub d is less than or equal to 0 against the alternative that mu sub d is greater than 0. So we have a one-sided alternative, as you can see, okay? And you know that mu sub d represents the difference mu1 minus mu2, okay? So we have step number 1. We know that step number 2 is finding the posterior distribution, right? Step 2, finding posterior distribution. So we know that the posterior distribution is going to be normal, right? After what we have here, right? We know that it's going to be a posterior distribution, normal with these parameters, no problem, right? Okay. So that's what we would have there. Then step 3, we know, is finding the posterior probability of H naught. Okay, so we have that guy there. So the posterior probability of H naught would be just the probability that mu sub d is less than or equal to 0, right? Given this, given that posterior distribution. And then once you have that, you just compare that to your significance level if you have one, and if not, to just compare the posterior probability of H naught with respect to the posterior probability of the alternative and see which one is more likely, right? So step 4, you make your conclusion and you're done. And that's it, right? So really simple. So what you know about this kind of procedure, this kind of method, when you were just considering one single sample, it still applies here, right? It's going to be useful. The ideas are basically the same. Now, what if instead of that kind of alternative, you wanted to consider a two-sided alternative, right? What if you had a two-sided alternative, meaning mu sub d different from 0, and then the null is that the difference is 0, right? So in that case, we know, right, that there will be a problem. I mean, there will be no problem up to this point. You're going to be able to find your posterior, no problem. But when you want to find the posterior probability, that's where you're going to be unable to do that, right? We can't, because the posterior probability of a single point is 0, right? We have a continuous random variable here, a normal, so the probability that a normal is exactly equal to 0 is 0, right? So we know that what we have to do there is we use the credible interval for mu d, and then if 0 lies in the interval, we cannot reject the null hypothesis. Okay? So let's just say that. So instead, we use the credible interval for mu d, and then if 0 lies in the credible interval, we cannot reject H naught. Make sense? And if it is outside our credible interval, then we reject. Okay? So again, the ideas that we developed for the one sample problem, right, when we were considering only one single parameter mu, well, they can be used here. Okay? So let's summarize what we did here together. So we considered two independent samples from normal distributions. The assumption is that sigma squared is known. Okay. We considered normal priors. Note that these ideas would also work. These ideas also apply for flat priors. Okay. So we know that in those cases, when the priors are normal or flat, the posteriors will be normal, right? So since we have independent samples and the priors are also normal, then when we want to say something about the posterior distribution of the difference mu1 minus mu2, right? Well, this is going to be just the difference between two normal random variables that are independent. We know that the distribution of that difference is going to be normal. These are the right parameters, right? Mean of the first one minus mean of the second one, and then the variance of the difference is going to be the sum of the variances, and we were able to obtain that formula for the credible interval for the difference mu1 minus mu2. That could be useful when you want to carry out a hypothesis test, a two-sided hypothesis test like this one, right? If, on the other hand, what you want to do is to carry out a one-sided hypothesis test for this situation, for the difference between mu1 and mu2, then you do basically the same thing that you did before for a single parameter mu, right? Step number 1, you state your hypothesis. Step number 2, you find your posterior. Step number 3, you find the posterior probability of h0, and then conclusion, you just compare that posterior probability of h0 against your significance level. If that posterior probability is less than alpha, your significance level, you reject h0. So same as before. Okay? Well, thank you so much for watching. Please take care and keep working hard. See you next time. Bye.